Welcome back. Today we're going to just talk about some sulfur compounds. Epoxides we've already talked about, but just a little bit of review there. Sulfur compounds, we don't really talk about them that much, and you wonder why. And that's because if someone's using sulfur in the lab, it's time to clear the lab. It smells so bad, okay? A lot of the time when things are rotting and you're getting a rotten egg smell, that's why they used to pelt people with rotten eggs, because the sulfides that come out of it are so rotten. So that's one of the reasons we don't do too much sulfur chemistry, because everybody in the lab's going to hate you. But let's look at some of them though. So sulfur compounds, you can have so many different types of compounds. This is H2S, that's the guy that's the stinkiest. And then you can have one of these, just like water, you know, the same group, you can replace these hydrogens with R groups. So let's say you can have CH3S, SH, methyl sulfide. And this is what they put inside natural gas, because natural gas, CH4, has no odor at all. And so if there's a gas leak, you could die because you don't really know, there's a methane leak. So they put some of this stuff and it stinks so bad that it's even going to wake up the dead. So methyl sulfide, that's what they have in natural gas. You can have some RSH. You call them, sulfides. Then you can replace, just like this is like an alcohol equivalent. You can make an ether equivalent, a disulfide. That's a thiol, just like alcohol. Sulfur is like thio. So thiol, this is sulfide. And in proteins, you get lots of disulfide bonds. So I'm just putting CH3, it could be any R group. For sulfides, CH3S disulfide linkages, like in your hair, you have lots of disulfide linkages that determines how curly your hair is. Disulfide. Then you can add oxygens. You can, unlike oxygen, here the sulfur can get oxidized, and you can get sulfones, and you can have some R group here. And we saw that with DMSO, when these R groups are methyl, then that will be DMSO. And then we can put two oxygens, take this and oxidize it, and you can put two oxygens there. So sulfoxides and sulfones, dimethyl sulfoxide. And the common one is DMSO, when the R groups are methyl. So those are some of the organic sulfur compounds. Well, how do you name this? If you want to order it online, you definitely need to know the name. So here, let's say you have this. So 1, 2, 3, 4, 5, 6. Hexanol would be the alcohol. Hexanethiol would be the sulfur equivalent. So here, let's say I have a methyl. And so sulfur is number 1, 5, 6. So this is going to be hexanethiol. Just think about hexanol. If the SH group is in like the middle, let's say you have both alcohol and an SH, this would have higher priority. So you start numbering from this side. 4, 5, 6, 7. So now thiol cannot be the suffix because the higher priority is oxygen. So alcohol would be the suffix for that, because the highest priority group always gets the suffix. You know that in naming, right? So this is heptanol. So this is 6-mercapto. So when it's a side chain, we call it mercapto. 2-heptanol. If you had an alkene, you call it heptenol, and so on. So thiols have this sulfur, and sulfur we learned when we did SN2 reactions. We said that was one of the best nucleophiles. So how do we make a nucleophile out of that? If it's neutral, then it's not that hot. If you want to make it really a good nucleophile, you can take your thiol or whatever R group here, SH, and you can put sodium hydroxide, and you can make that into an anion, because the OH is a lot more basic. SH, this is actually slightly acidic. So this is going to come in and deprotonate that, and you will make a weak nucleophile into a strong nucleophile now. This is a really good nucleophile, one of the most powerful nucleophiles out there, plus water. So now you can take this and do SN2 and so on. So let's say I want to go from thiol to sulfide, then I can bring in another R group with a leaving group. So let's say I can bring in an ethyl or a methyl. You don't want to bring something tertiary, some primary methyl iodide, let's say primary or secondary at best. You don't want tertiary because it's an SN2. So here's a nice backside kick, and the iodine is going to be on its way. And that is going to give you a sulfide from a thiol. Plus the iodide then goes off with your sodium. So that's a very easy way of making sulfides from thiols. So that's going to precipitate out, and you can distillate out. These are very low boiling. There's no hydrogen bonding because SH is not very polar. Sulfur is not very electronegative. It's almost about the same as carbon, really. So it's not very electronegative, and so therefore this is going to be very low boiling, and you can boil it off. Obviously, when you have longer chains, then London dispersion forces play a huge role in increasing the boiling point. If they want to make disulfide, then they take the same thing. They will take, say, let's do a different one, sulfur, and then they will put sodium hydroxide and make it into thiol. Take this same thing, and this is kind of abundant, so you can make that into a sodium sulfide. Then you can take this and you can put some bromine or some good leaving group. So let's say I put bromine in here plus Br2. You can do an SN2 kind of a reaction right here with the bromine and create a good leaving group on the sulfur. So your sulfur now has got a good leaving group. Just like you can have OCl bond SBr, these are more stable. As I said, sulfur is not very electronegative, so the overlap here with the sizes are quite good. Now, even here, when you take the sulfur oxygen bond, the sulfur and the oxygen have very different sizes because sulfur is third period and has got d orbitals, oxygen's the second period. So these bonds, the sulfur oxygen bonds, double bonds, are really not as strong as a carbonyl, carbon double bond oxygen. So in these cases, the resonance form is a lot more significant. You can take this and now you can do an SN2. Let's say you want to make a sulfide, then you can take this and let's say you can bring in another one of these, or you can bring a different one, but I'll just make the same one and do an SN2. Make that into a leaving group and you can get a good disulfide linkage. Plus, let's say you came along with sodium and you get sodium bromide falling off, and you will take a thiol to a disulfide. So this is thiol to sulfide, and this is thiol to disulfide. To go from a sulfide to a sulfoxide or a sulfone, we have to oxidize them. So we can take sulfide here. There you have R, S, R, and you want to go to sulfoxide or sulfones. You can oxidize them. Sodium periodate is going to put one oxygen on there. And if you put peroxide, is very strong oxidizing agent. it will take off both lone pairs and oxidize them to sulfones. So that's one reaction that's typically done in this case to make DMSO and so on. So if you bring R equal to methyl, you can use this method to make CH3SO CH3 DMSO, which is a very big solvent in industry. One other thing that these things are useful for is for putting a methyl cap. So let's say you want to put a methyl on a group, you use these as like a carrying agent. So let's say I have a sulfur here, and I can put a methyl on here using methyl iodide. So I'll take methyl iodide and I can put this here temporarily because there's no hydrogen here, so you can't really deprotonate to make it neutral. But this is kind of an intermediate form. So here you put a methyl group on here. You lost a lone pair, and so now you're 1, 2, 3, 4, 5. 6 minus 5 is +1 oxidation state. And so that's an intermediate. That's really not a final product. And so you have an I minus there. So this intermediate can then be used for putting a methyl group on other groups. Let's say you bring in nice nucleophiles. It could be SH or phosphorus or carbon. Let's say I put cyanide in here, Kc, and let's say deadly toxic stuff. But you can put a methyl and make acetonitrile. So here's Cn, and you know acetonitrile is a very useful solvent. You can take this, hydrolyze with sulfuric acid, and then it's be carboxylic acid, and you can just throw it down the drain. So it's not really very toxic. And then you will get potassium iodide, and then you can take this sulfur again, you can retrieve that, and you can go back and do the same thing. So it's kind of a carrier to put a methyl group on a nucleophile. So I would say any nucleophile, good nucleophile. It doesn't have to be cyanide. I'm just taking cyanide as an example. Could be anything. So that's another very useful process to make acetonitrile or things that need methyl on it. So I'm not going to talk too much about sulfur. As I said, they're not very sweet smelling, and people do avoid using them in lab. But the biggest use for them is probably in the natural gas industry, where they put this along with natural gas. So when you smell it, you wake up. Wake up and smell the coffee. So here, let's do epoxides. And we have done epoxides when we did alcohols, but let's look at a little bit about epoxides. Epoxides, we said, were made with MCPBA. So that's one way to make them. So here's an epoxide, and you can take MCPBA and put an oxygen on that double bond. And we've done this mechanism before, so I'm not going to redo it. But there are other ways of doing this too. You can take a alkene, and let's say I take this alkene, and here you can do a addition and elimination. And this is something you've already done before. Bromine in water. So bromine water, you know, is going to add bromine up and down, and then the water is going to add to the more substituted position because it's Markovnikov, and it prefers to attack the tertiary because the parting group will leave a positive charge more stable at that position. So here you're going to put a bromine, and I'm just going to put the bromine here, but it can be up or down. And then you are going to take water and open it up. And your bromine can be either up or down. So let's say your bromine was up, then the bromine will go up, and the water is going to be down, and then your methyl is going to be popping up because it's attacking from below. Now this is then going to get deprotonated, and we've done this before, but I'm just doing it, to bring this back to memory here. And now you are going to take this OH, and the OH is on the opposite side of the bromine, which is what we really want. That's important. Unless it's anti, this is not going to happen, and we know that this is an anti-addition. So here is up, and here is our OH. Well, OH is neutral. It's a weak nucleophile, and so it's really not going to attack bromine. So if you just put in a little bit of sodium hydroxide here, sodium hydroxide can do many things. It can do E2 here, and here are side products. It can do SN2 here. But because this is an acid, acid-base reactions are really very quick. So this is a pKa about 16, slightly more acidic than any of the CHs out there. Sodium hydroxide, if you put just very little sodium hydroxide, the first thing it will do is deprotonate this, because that's the fastest reaction. So it's pretty much kinetics. So now you're going to take that O minus, and once you have an O minus here and a Br up, these are anti. See, it's internal SN2. So you can hammer it from the bottom and take that up. So if I draw these out like this, it might be more obvious. So you have a methyl, and you have an O minus here and a Br up. So you can hammer it, and you have a sodium plus here as a counter ion, and then you also form water from the deprotonation. So you can take this and you can go bam and take that out. You got a really nice epoxide, and all the reagents are pretty inexpensive. I mean, pretty cheap. So you can buy them dime a dozen. So there's your epoxide. Now I only drew one side. This is Cairo, and so you can get up and down. So I'll just put plus minus. So you get plus and minus here, 50-50. That's good, but sometimes if you're into drug synthesis and so on, if plus is good for you, minus can be bad for you, maybe. So you don't want to make both. So then what they do is they take a Sharpless catalyst that they throw in that'll only make plus or minus, not both enantiomers. So here you're going to get enantiomers, and that's not that great. So if you want only one of them, you want to throw in a catalyst, and that also only works on allyl alcohol. So here's an allyl alcohol, and I really don't have that much space, so I'm going to skip the mechanism here. And you use titanium isopropoxy catalyst, and then you also put in something called DET, and that's an ester CH3 CH2O, and here's a OH and an OH, so you can have plus and minus. It's like tartaric acid. You can have plus and minus OET, I'm going to put. And if this is positive, then you will only get one of the epoxides. Here, if you put positive, it's, let's say, gives you up. And if you put negative, which means that both OHs are going inside the plane, then you will get the one that's going down. And then the OH is still there. And if you want, you can do other reactions. So this is enantiospecific Sharpless catalyst. Sharpless is a chemist. Got a Nobel Prize, I think, for this. So that's one way to do enantiospecific reactions. What are the reactions? And we studied a ton of reactions with epoxides, and I'm not going to repeat them. But if you have an epoxide, it depends on the substitution. If it is substituted more on one side than the other, let's say you have two groups here and one group here, or one group here, no group here. If it's asymmetric, then it can go either way depending on your reagent. So if you have acid reagents, acidic conditions, then it's going to attack the more substituted. A. Attack A at A. If you have basic or anionic, anions are kind of basic, anionic, then it's going to go B. SN2 like, and this is SN1 like, and that's why the difference in the position, because if you put an acid, it's going to protonate it first, because the oxygen's got 2 lone pairs and it's just happy to protonate, let's say with an H plus here. When you're breaking that bond, you want to break it here so there's a tertiary that can bear that incipient positive charge. You don't want to break it here and create like a primary. If you break it here, it'll be more like secondary, or if you have 2 groups, it'll be more like tertiary. And so therefore, your incoming group, let's say an ROH, so this is another way of making ethers, is going to go here and push that up. And so now you will have a OH group here, an alcohol, and I'm going to put another arrow because I don't have space to write the deprotonation, and you will get an OR group here. So here's an ether, so alkoxy, let's say 1, 2, 3, propanol. So 2 alkoxy propanol, or some alcohol. It could be any number of carbons, ether, and an ROH. When you have basic conditions, let's say you want to bring in a nice sulfide here, they're going to go seeking the less substituted position because there's less steric. There's no protonation there, so you are going to have to open it up all on your own. And why would you go fighting with these big groups here? There's a lot of steric here. And so therefore it's going to avoid that and go say hello to the less substituted. So let's say I'm going to bring this sodium sulfide. It's going to go here and open it up. And it's going to make a sulfide. So here you're going to have your O minus, and then you're going to protonate that with just water, or I'm just going to leave it there. And you know, if you add H plus, it's going to wash out your salts, and you will get your sulfur here. So that's using epoxide, and it could be any nucleophile. Basic anionic nucleophiles. So if you use nucleophiles, they're going to attack at the less substituted. If you have acidic conditions, it's going to go for the more substituted. That's kind of the take home here. And I'm going to put just another arrow, and let's say H2O or H3O plus, and we can take off this sodium and put a hydrogen. I know I'm cheating, but I'm out of space here to write that extra step. But you know how that is. You're just going to protonate that oxygen with the water. All right, guys. So that kind of concludes alcohols, thiols, epoxides, and so on. And I will see you next time for a very new topic. All right, guys. So bye.